Okay, we're working on number 19. We just finished the first derivative test. We're now going to work on the behavior of the second derivative. You must have all domain restrictions on any of the number lines, so I will get back to that once I find the critical point. So I'm going to look at this to see what we've got going on in terms of the critical point. Now remember, the critical point occurs when the second derivative is equal to 0 or undefined. So since this is a constant and no variable, it's impossible for this fraction to equal to 0. It is possible for this fraction to be undefined at 4, but 4 has already been taken in by the domain, so we can't use that as a critical point. It can't be in both. Alright, so that means that there are none. Which means that the only thing that's on your graph then is, in terms of points, is your 4, which is your domain restriction. And again, make sure that you don't say any conclusions about it because there's no graph there. Right? Don't forget we have that. That has to show up on your number line. Alright, so I'm going to use to the left of 4, I'm going to use a test value of 0. To the right of 4, I think I'll use 6. So for this one, the 8, since it's a positive 8, you want to note that the numerator is always positive. The denominator can be positive or negative, depending on what we're plugging in. Alright, so here we go. So we just said the numerator is always positive. If you plug a 0 into the denominator, that will ultimately be negative. So positive over a negative is negative. Alright, that means it's going to be concave down on that segment of the domain. Alright, next we picked a 6. Like we just said, the numerator is positive. If we plug a 6, the denominator will be positive also. So overall that fraction is positive. Okay, which means that on this segment of the graph, the function looks concave up. Alright, so let's write what we found out from our investigation. So now we know that the function is concave up on 4 to infinity. We know that the graph is concave down on negative infinity to 4. There are no critical points, and because there are no critical points, it's impossible to have an inflection point. You cannot have an inflection point around a domain restriction, which in this case is a vertical asymptote. There's no graph here. There's no point here. So in terms of inflection points, our observation is that there are none on this graph. Okay, so let's now get to the business of drawing it. I'm going to take a moment just to look at how big or small my numbers are. So like I'm taking into account what the size of my max and min is, and I'm taking into account my VA and my asymptote. So I'm trying to get a sense of like how big this graph is going to end up being. Alright, so none of the numbers are like ridiculously huge. Alright, so I'm going to start with, okay, so I'm going to make this a 1, like this is 1, 2, so on. I'm just trying to figure out like the magnitude I want to make things. So I'm making this a 1. A magnitude of a 1. Alright, now I'm going to start to put up some of my information. I know that I have a vertical asymptote at 4. I know it's odd if you remember that from pre-calc. Again, that means it's going to go in the opposite direction. I know I have a slant asymptote at y equals x minus 2. Now, sometimes students get totally confused when they see this, but if I told a algebra class to graph y equals x minus 2, they would graph it. You guys just forget because you think I'm writing something fancier than I am. That is just a straight line. You're just graphing a straight line like you would in algebra. So don't blow this out of proportion. How you graph a straight line is you graph the intercepts. So like for instance, if x is 0, y is negative 2. If y is 0, x is 2. That's how you graph a line. You do the intercepts. Alright, so I'm going to plot the intercepts. So I just found the 2 points, 0, negative 2, and 2, 0. Right, you can always add more points if you want. You can add a third checkpoint, but 2 points is enough to graph a straight line. It's just a line. I'm just putting dashes because in calculus it's an asymptote. In this case that I'm drawing. Okay, so this line, this slant asymptote is y equals to x minus 2. Okay, now let's start putting up the actual points for the function. So we have a relative max at 2, negative 2. Okay, so that's 2, negative 2 would be here. That's a max. A relative max. And we have the point 6, 6, which is a relative min. Great. Okay, so the idea is that the graph will ride the asymptotes. The graph will ride the asymptotes. You know, what would be a really nice thing to have on here also would be the y-intercept. You may have noticed it doesn't have any x-intercepts. This will solve out complex. So it has this graph has no x-intercepts, but it has a y-intercept. Remember, to find the y-intercept, you just let all the x's equal to 0. So you have 0 squared minus 6 times 0 plus 12 over 0 minus 4. So you're going to end up with 12 over negative 4, which is negative 3. So it's 0, negative 3 is your y-intercept. And again, no x. Okay, so the idea is, as you come from negative infinity, your graph is increasing to its maximum and it's concave down. You're going to hit your maximum, it's going to start to come back down. As it comes back down, it's still going to stay concave down. Remember, you're looking at this simultaneously. Here's the 4, right? The 4 lines up here. So this whole thing is, both these things are happening to the left of 4. So what that looks like is the graph is increasing, but it's concave down. Make sure you go through this point. It has this y-intercept. The max means this is its highest point, so don't go higher. This little part doesn't go higher. Okay, it's going to come around and it's going to ride the vertical asymptote. So that part looks like this. Now odd means it goes to, so if it's odd, it means one side's going south, so that means the other side is going north. So the other side will actually be up here. That's what an odd VA means. They're going in opposite directions. Now if we look back at this, now we're on the right side of 4. On the right side of 4, the graph is coming down, but it's concave up. It hits its critical number and it starts to increase, but it stays concave up for the whole ride. All right, so that means that I'm going to come down. I'm going to hit my critical number, which is a minimum, so do not go any lower. And then I'm going to head back up. All right, so, and this is concave up. This would hold water, this would drop water. So this is strictly concave down, this is strictly concave up over here. And that's why you have like, can you see like for locally, for this half of the graph, that is actually the highest point. For this half of the graph, that is the lowest point. So locally, this is a minimum, and locally, this is your maximum. So it does actually work out. Okay, gang, that's it. That is number 19. I'd say this one's a real heavy pre-calc to solve this. So you're going to see a lot of the pre-calcs going to come up in the graphing. Okay, catch you. Bye-bye.